Thank you for having me. Obrigado. How many of you have heard of deep learning? Hands up. Oh, awesome, everyone. Almost. Forget about deep learning. I'm here to tell you about something better than deep learning. Just quick disclaimer. So not only you have heard of deep learning, but in the media, social media, and everywhere, basically everyone is telling you that deep learning is the best machine algorithm ever. So it beats all these other like traditional machine learning algorithms. And then it beats humans at games, and it's probably gonna take our jobs, and then maybe later it's gonna destroy us all. So I have a pretty more nuanced view on deep learning. Indeed, deep learning has had tremendous success in computer vision, in image recognition, also some success in natural language processing, and combined with reinforcement learning, it has indeed tremendous success in virtual environments such as playing games. However, I don't think deep learning is AI, or maybe it's never gonna be solving AI. And also there is all these other machine learning tools we have been using in businesses, in the industry for, I think, over 30 years. In many business domains, such as fraud detection, credit scoring, marketing analytics, manufacturing, telecom, insurance, and many other business problems have been solved by traditional machine learning for over like 20, 30, or even more years. So I tried to look at how about if I try to use deep learning in some of these domains, and I happen to work in one of them, but I cannot talk about that. But I did also like try to fit deep learning and beat these traditional algorithms on some public data sets. So here is one in 2015 that I put on GitHub, is the airline data set. And I talked to deep learning experts, and really they helped me try different architectures and trying to beat this old school machine learning algorithms. And on these data sets and many other this kind of businessy, structural tabular data, it's not actually deep learning that's the best. But I think a better clue of what's going on is if you look at Kaggle. So here's Tianqi Chen talking at one of the meetups early in 2016. He has looked at all the Kaggles from 2015, what kind of algorithms people have used to win the Kaggle competitions, and in 2/3 of them, it was actually the gradient boosting machines that had been used in combination with many other things, but not really deep learning. So I think this is kind of my version of the slide of which algorithm is best for what. And since then, even Kaggle CEO Anthony is talking at various conferences about that for structured tabular data, actual gradient boosting machines beat deep learning. But for some of us doing machine learning for many years, like I do it for 15 years, this is not new and it's not really surprising. So there are these two papers from 2006, and they had looked at many algorithms, many data sets, and random forest gradient boosting and neural nets indeed has been the ones that achieve the highest accuracy. And I happen to have used gradient boosting and random forest since 2006. I didn't really know about these papers, but I kind of tried all these algorithms on my data, and random forest and gradient boosting have worked the best. So my advice on what to use is if you have tabular structured data, typically in like a business environment, coming data from databases, then try random forest on gradient boosting. If you have small data like 100 observations, try really some simple models like linear models. Everything else would probably overfit. If you have huge data sets like billions, trillions of data points, probably anything else again than linear models would not work because it will take too much computation. And if you have images or speech, yeah, do use deep learning because deep learning is really the best in this domain. So actually the truth is that it depends on a lot of factors. So I think I have to tell you that my title was a clickbait. It's gradient boosting is not better than deep learning. It's better for tabular data, but deep learning is better than gradient boosting for images. So it really depends. You can also try them all. So there are like 4 or 5 machine learning algorithms. You can just basically try them all and see what works the best on your data. You can do hyperparameter tuning, spend a lot of time optimizing these models. Then you can also get better accuracy. Do ensemble. If accuracy is paramount, like in a competition, then you have to train hundreds of models and combine them. And that also can boost the accuracy. But actually, what's surprising is that it's not very sexy, but actually, sometimes the machine learning algorithm doesn't matter as much as feature engineering. So domain knowledge matters very much, and sometimes the accuracy, you get a boost in accuracy by adding some new variables or some new data, some new features. And sometimes accuracy is not really the most important things. For instance, there are some domains where you have to have explainable models, and sometimes accuracy is not really the most important. So with all this, let's talk about gradient boosting a little bit. So another name would be gradient boosted trees. So we start with trees, decision trees. Probably everyone knows what's a decision tree. And then we build iteratively many trees, and we're gonna average them. So the idea of boosting, you don't need to read this, is that basically you build trees, and each tree is gonna try to focus on the observations that the previous trees have misclassified. And this is very powerful algorithm, and it seems like it's kind of working. So if you want to use gradient boosting today or tomorrow when you go back home, there are many packages, open source, that you can use. So I had this problem a few years ago, and I didn't know which one worked better. So I did like a benchmark that's on GitHub. You can take a look at that. There are scalability graphs like this. So I looked at training time, which one is faster, how much memory they are using, and this kind of things. So I would just jump to the conclusions and show you that basically the conclusion is that those 3 open source implementations are the best. So xgboost, it's been used a lot in Kaggle, H2O, and then a newer open source library lightgbm. And all of them are available both from R or Python, so you can just install it in 1 minute and start working. Some people might ask, why not Spark? So Spark, unfortunately, is like 10 times slower than the best ones, and it also uses 10 times more memory. So kind of it's not really the best tool to use if you want to do gradient boosting machines. But you would tell me that, hey, but I have a lot of data. No, probably you don't. There are actually surveys that show that most people in analytics work with data that fits on one server, so it's not really that big. Data is big usually when it's raw data. So for instance, think of clicks. But once you refine it and you feature engineering, you get to some smaller refined data set that you use for machine learning, like a data matrix. And that's usually not as big as the raw data. So it's orders of magnitude smaller. So it surely fits on one server. And now it's very easy to get a lot of RAM. It's very cheap. You can also get on the cloud. You can get hundreds of gigabytes of data, even terabytes of data. So surely all this will, surely your data matrix will fit on one server, except maybe for a few use cases. And I think this has been controversial since I've been giving this talk or versions of this talk or predecessor of this talk for maybe 4 or 5 years, and it's been kind of controversial. But by now, I think people have realized that they don't really need to do their machine learning on bigger data. They don't need these tools. They just want tools to be faster. So why do we need fast? So first, we do a lot of cross-validation. We do hyperparameter tuning. We do ensemble. So we train hundreds of models. We need to be able to quickly iterate over this. So if running one model takes hours, we're not going to be able to do this unless we spend a lot of money on infrastructure or cloud. So I redid a little bit my benchmark so that it's concentrating now just on GBMs, and I also made it very reproducible. So there is a Docker file, so you can run all these numbers. So basically, I looked at the training time and of some of these best open source implementations, and if you're running it on a CPU, then currently lightgbm is the fastest. They all have GPU implementations, so if you have a GPU, then probably xgboost will be faster on GPU than lightgbm on CPU. So if you have a GPU, try xgboost. And same for the memory usage, so the same tools are kind of the best. However, if you need to put your models in production, my favorite is H2O, because with only this many lines of code, you're up and running with a prediction service that can score through a RESTful API. And API matters, so even for training, you want to be a lazy data scientist, so you don't want to write like hundreds of lines of codes. So all the three products, or open source products, they have very nice APIs. So you write a few lines of code, and then you have train, and you can use the model for prediction. By the way, gradient boosting machines are pretty complex. They have a lot of parameters. So if you want to tune them, I recommend here two blog posts, and you can find a lot more on the internet. So one thing I would recommend is do early stopping. This is something that got into this open source libraries maybe 3-4 years ago. So by now they're all standard. So if you train too much, gradient boosting is gonna start to overfit. So you have to stop somewhere, and then the way to do it is to look at the error on the validation set. But all these libraries, they made it really easy. So you just have to specify a few parameters, and it's gonna do the early stopping for you. So here is some kind of summary of comparison of this library. So the gist would be, if what matters the most is short training time, and you don't have a GPU, then use lightgbm. And if you have a GPU, use xgboost. And if training time is not that important, it's more important to put your models into production easily, and you need this kind of fast, real-time, non-batch scoring, then I would recommend H2O. But again, it depends. So there is a lot more into it. I will give you some references later on. I think by now people have kind of figured out that these three are the three best products to use for gradient boosting, because basically I did a survey over 100 people, and then basically these are the software tools that most people are using. And this is kind of the way how to get the best accuracy and to win competitions, such as this one at Kaggle Days, was in San Francisco recently. So basically, we talk a lot about machine learning, but actually most of the work is in this feature engineering and learning about the data and cleaning the data and all this stuff. So that's the unsexy thing that we don't really talk about, but we spend most of the time, probably 80% of our time, with data cleaning and feature engineering. You need to do that. Then you probably want to train a lot of gradient boosting machines. For example, this is actually screenshots from a blog post from the winners. And they trained lightgbm a lot of models, and then once they kind of knew where they are, they also trained a few other models like xgboost and random forest and even some neural nets. And then the recipe is basically take all these models and combine them, ensemble them into a final model. So this is basically how you how you win competitions, how you get the best accuracy. So all I wanted in this talk is basically convince you that if you work with tabular data, structured data, on typical business problems like fraud detection, credit monitoring, or credit scoring, churn in telecom or insurance, then probably you don't want to just do deep learning as everyone is telling you, but you want to try random forest and gradient boosting machines. And if you don't believe me, then here to Yoda, he's saying the same. So I gave this talk like a longer version. I had to cut out a lot of the technical details. So if you're interested in more technical details, then find my some of my videos on YouTube. There is a lot more talks on this GitHub repo, and then there is a lot more GitHub repos. I made public whatever I found about GBMs, so you can look all this up, and that's pretty much for now. So feel free to talk to me. I'm here all day, so feel free to talk to me in the break, or if you cannot somehow find me, then shoot me an email or on any of those channels. I'm happy to interact. So especially let's fight if you think that deep learning is the best.
Thank you.